This will be an update on where we're at as of November 9th, 2018 for reference on drone technology. We're going to talk about where we're at from a technology standpoint, and then we'll talk a little bit about image processing and analysis, and maybe a final product that could come out of that process. So if you look at some of the technology that's available today, there's basically two platforms that most folks are using in a commercial setting when it comes to agriculture and capturing imagery. That's either a fixed wing, such as this Parrot EB SQ, which is around $12,000. When we talk about these type of fixed wing systems, we need to consider that you will need some space to land specifically and possibly to take off from that standpoint, and then you're probably going to need a dedicated, in the case of the fixed wing systems that we look at, probably a dedicated laptop or some type of ruggedized tablet that's running a Windows operating system platform for our mission planning to allow the drone to fly its missions. You will notice on this one you're going to get close to an hour flight time and covering, upwards of 500 acres. Again, that depends on the above ground level that you would be flying. Here's a little bit cheaper model. There's a company out of Dayton, Ohio called Event 38. They manufacture a few fixed wing aircraft. I just thought I'd show some different ones here. About a four foot wingspan. That EB had similar, a little bit cheaper price tag. And then you're going to use, in this case, you've got some different options from a camera standpoint, as well as the EB. Here, I'm just showing you a point and shoot that will be modified to capture imagery as we're flying. You get a better feel for that as we go through the presentation. Here's an example of that presentation in a Windows platform to create your mission planning. You can see the red boundary here in this platform. I think we've got a short video that sort of shows you've created the waypoints. Most of the fixed wings you would launch and throw them, if you will, into the air from that standpoint, and then depending on the sensors you can get different information that's out there. And then it's landing out there. When I say landing, you're going to need some flat surface, preferably a grassy area to land these fixed wings that we're showing you here. Another sort of hybrid fixed wing that a couple of different situations here. This is called a Firefly 6 Pro. It's being offered through Precision Hawk, which sort of puts the pieces together, if you will, from a mission planning, partly image processing, but those propellers and the motors are movable, where right now they're in the operation would be where that would take off, and then they would rotate to push the aircraft through the sky. Sort of a flat rate to begin with is about $6,700 for that specific drone, and you can see not quite getting 50 minutes. It depends on how much payload, how much weight the camera system, sensor system that you have. 60-inch, 5-foot type wingspan, give you a frame of reference of how big the aircraft is. Here's another one that you see here that's sort of the same type of system. It offers a couple of different ports. You can see up there in your upper right hand corner for maybe a couple of different sensors, camera systems operating at the same time. But it also operates, the rotors don't actually rotate, it's the aircraft that can rotate, but the price tag's a little more expensive, $16,500. Then we'll get into some quadcopters, several different ones. I'm going to show you sort of DJI sort of has cornered the market, but there are a few others out there. This happens to be one, and I found it offers a sensor platform that's sort of ag specific from slant range, but you can see some different pricing. Again, the operating system is a Windows-based system for the mission planning, but some of the quadcopters through this action drone can get up to 45 minutes of flight time, depending on the battery system and the drone itself. And here, towards the end of 2017, America Robotics came out with a totally autonomous drone where this box and the quadcopter is sort of all in. You'll notice that the crop behind the drone is grape, so a high value crop where you might have this in a vineyard and you have it programmed to maybe fly every day or every other day or what have you. It charges itself, collects the information, and it's sort of completely totally autonomous where you're not going to do much hands-on with it. DJI, I just mentioned that before, is sort of has cornered the marketplace a little bit. Different models that are out there. Most of the stuff that you're going to see in the rest of the presentation is captured by a Phantom 4 Pro or a Phantom 4 Pro version 2. That version 2 just came out towards the first of the year. It offers a few different tweaks over the Pro. Cost about another $500 that I haven't seen. I've got both in the fleet that I have, and I haven't seen any really benefits above the Pro for the imagery that we capture and those kind of things. A couple of other platforms that are out there is a Matrix 100. There is a 210 I haven't mentioned, but I think if we're looking at for the price tag and what we can afford in agriculture to get started, you sort of look at that Matrix 100 and how it can offer some advantages of putting different sensor platforms on it, as well as Inspire 2. Some newer compact drones that are out there that offer, DJI introduced the Mavic Pro a couple of years ago. For the price tag, it offers a good entry point. You can fly it autonomously and capture information across the field. From that standpoint, you notice a company name that I've put there, flyingag.com, puts some packages together for some of these DJI drones that is a good way to go, that have batteries, case, everything in a package deal. So that gives you some idea on price. You can probably use Amazon.com and have it a little bit cheaper price, but it gets you in the ballpark. The DJI Spark is really the bottom line of an entry drone. Really the only thing you can do that is sort of some targeted scouting that we'll talk about later in the presentation. And then another sort of entry point drone that was introduced sort of about a year ago was a Mavic Air. And it's a pretty good little drone. You can fly total fields with it. It does have, because of its size, a little bit of limitation of wind from that standpoint below the Mavic Pro. And then just introduced, and I haven't really completely, the Mavic Pro 2 was just introduced. It's got some couple of different versions from a camera standpoint. It does have a camera that will zoom. That may have some use in agriculture from more of a scouting standpoint, but I just mentioned that one also as far as some other alternatives, and we'll mention some work that I've done with the Spark and the Mavic Air from a scouting standpoint a little bit later on in the presentation. So where can we start? Here's an example of maybe what that $600 drone or that $1,000 drone could do for you. This is some imagery that we first captured with the original Phantom 1 drone and a GoPro camera. But you can see, if you're looking out sort of over the field, you can see some different things in this field, from the 3 streaks that go down through the field that are a little bit lighter colored corn that have been, we discovered that was a fertilizer issue, the quality of the fertilizer. There's too many fines in it, and we didn't get as high enough nitrogen rate right out of the back of the fertilizer spreader as we would across the field. But that was the starting point. But you want to probably go beyond that and be able to capture imagery of the entire field. And to be able to do that, you first of all have to have a drone that's capable of flying autonomously with a mission, and then that drone captures imagery. So this is just an example of a wheat field in March, and that image is made up of 215 images flying at 80 meters above ground level, and there's about 60 acres encompassing that area. So how does that done? We've been utilizing a few different apps. The main app that we have utilized is called Map Pilot, and it is specifically tied to DJI drones. All the drones that I have mentioned in a DJI class, except for that DJI Spark, the Mavic Air will fly with this drone, as well as the Mavic Pro. It's $10. What it allows you to do is lay out a mission. Those yellow orange dots are dots that you tap on, in this case an iPad. You can run it on a iPhone. It is an iOS app. We have settled on the iPad mini as sort of the best application. We've used regular size iPads, as well as even I've experimented even with an iPad Pro that's got 12 plus inch screen on it. That's a little bit harder to manage on that, but can be used for demonstration purposes. So you put those orange dots on the screen. You need an aerial photograph. You can do this process in the office and then save the mission, and that saves the images of that field as a reference, and then you fly it. You'll notice that the green dot is where the start of the mission is, and you'll notice up there it says batteries 3. That means it's estimating you'll need 3 batteries, because the DJI Phantom 4 battery life is only about 20 minutes, to maybe a little bit more if you get lucky. So that's estimating that it's going to take just a bit beyond 2 batteries. And you notice there's a difference in coloration of that line, the mission line. That's where one of the batteries will expire, and the app and the drone is smart enough to know to fly back home, request a new battery, put a new battery in, and then it will resume the mission from that point and go forward. This is sort of what it looks like almost at the end of the mission, where each one of the little circle dots down the mission line are where the photos are. This is just in a different field that we were flying at 100 meters above ground level. We're flying about a little over 50 acres. That's 24.3 or 6 hectares. Took us a little over an hour, and took two batteries to do that job, and it took 299 pictures. That was doing that. So the nice thing about this app is you get some diagnostics information like that we just sort of discussed through. You also get a percentage of your, in this case, your iPad battery, percentage of the drone battery, percentage of the remote battery, how many satellites drone is receiving. The other one here with HD is a indication of transfer, video transfer. You'll notice there's a picture down here at the bottom as it was landing that was captured. So you can see that, and that's what that percentage is. And then over here you can see the distance that you flew. Another diagnostics that helps us out is this motion blur. We want to keep it as low as possible. That's somewhat related to speed of travel and how much wind that you're fighting to do that, and then it also indicates your flight time that you've been traveling. So if we look back, I'm going to probably skip back here. This is the field that we'll see in this next image here that we captured. And one of the things that we've been attempting to do is, instead of just a picture, can we turn that picture into a decision? So here we're using a process. Colleague Peter Scarf, who is our soil fertility extension specialist with University of Missouri, has developed the Envision Ag process that can turn aerial imagery into a side dress nitrogen application map. One thing about it, you'll notice these little red dots over here. That little square, which is about 16 rows by 40 feet by about not quite 200 feet, had 200 plus pounds of input on it. So that was used as a reference, and then the, if you will, the green pixels throughout the rest of the field were compared to what that looked like. And then this bottom map is a side dress map that we had. And you'll notice there's some sort of strips laid out over the top of the aerial photograph, and that was utilized. We were testing using the drone imagery, as well as some sensors on the applicator, as well as what the producer would have done. And that's what this is. So this is the producer, and he was going to put another 40 pounds of N on the field. And then our yields, the Envision or the drone image on average put 48, and the sensors on the applicator put 48. So the promising thing to me about this first go around, and this was in 2016, is that we were able to create a image. We were a little bit over what the producer would have done, but we had very comparable yields from that standpoint. So the technology seemed to be working, and we're moving forward to it. So I'm going to provide you another sort of system that we did here in 2018 that I got results from at a soil health farm that's located up in Sheridan County, Missouri. And some of the imagery, as well as how we turn that imagery into a decision aid. Excuse me. So this demonstration farm is actually made up of, you can sort of tell that there's 1, 2, 3, 4, 5, and then the bottom field 6. There's 6 fields. This year there were 3 fields we're going to be planted to corn. So this is before planting on April 23rd. 2 of the fields have cover crops, and then the bottom little field had just been vertical tilled a couple of times, and you can see how clean it is. So we have some different systems ahead of corn. Cover crop by itself, over to your right, to bottom cornfield, has cover crop as well as a wheat into the corn soybean rotation, and then the bottom field is a corn soybean rotation that has very minimal tillage done to it. So we were interested in seeing, using the same process as we just sort of mentioned before, a little bit in a different way. Is there a difference in nitrogen management or nitrogen need in those fields? So here's the 3 corn fields taken on June 11th. The corn's about shoulder high, and the drone was flying at 75 meters above ground level. So in this, a couple of things to sort of help you indicate, you can see down here on the upper right corn field, on the east side of the east corner of that field, you can see how green. That looks like the best corn on the whole farm. And you can see sort of a lighter color on the field that was conventionally tilled, and you can see some variation in color on the west field there. And taking that information and turning it into a nitrogen recommendation map. So you can see down there in that one corner, we're not going to apply any extra nitrogen. In parts of the field, we've got recommendations all the way up to 85 pounds. In a little spot here, there was 120 pounds pre-plant that were put on that field. So you can see how we did that. Well, we varied the rate across in some strips, and then compared those to a flat rate of 50 pounds. So you can see in this case, we were decreasing the rates of about 12 pounds per acre of N, and on the bottom field about 10. So in the end, could we capture any economic value by doing that? So we take another image. This was on the 29th. If we go back, these treatments were applied on the 13th of June. Remember, the image was taken on the 11th, and this is the 29th. So we see if we can still see any differences out there. And you can sort of see in the upper fields here a little bit of streaking. I think that is where the lesser amount of nitrogen was applied based on drone application. And you can sort of see that faintly in this. So we developed another map, and you can see the majority of the of that is in that maybe 20 to 25 at the most pounds might still be needed, except for down maybe a little bit in some spots in the bottom field. And then here's the yield data from the field. Should be noted that sort of directly after the 29th, even at the 29th, the corn was starting to stress, and the water shut off for a while and sort of hurt our yields in this field. But we still had some spots on the farm that yielded above the 155 bushels per acre. And if you notice over here on this side of the field, we're down, less than 100 bushel. Specifically, that's sort of a eroded side slope. If you refer back to here, that's where it was calling for the most nitrogen. Well, there's still probably some things that can be thought about that, you can only pour so much nitrogen on it to do, and it really does show that, even then it was still saying it needed more. Part of that is just the capacity of the soil itself from that standpoint. So if you truly look at all the yield information, fixed rate 122, drone base rate 120, 142 and 142. So these fields up here, we actually made money by decreasing the N rate by 12. The producers said that would have amounted to about $5 an acre left in the pocketbook. Down here, maybe not so much. Statistically, there wasn't any difference between 130 and 124, but As a producer would see that, that's $6 a bushel, and that's around $20 an acre in income of difference there. So, something to be said on that. So that gives you another real life example of something that we just got worked up for a field day that we had right before I finalized this presentation. A few other things that we can talk about. What drone do you use? All the imagery that you've seen on that demo project was collected with a Phantom 4 Pro. The 2016 picture was taken with a Phantom 3 Professional. You can look at this same field. We flew the same field with actually 6 different drones. I'm just showing you 4 different pictures. The 3 Professional, the 4 Pro, and the Inspire 1 version 2 look pretty similar. Even the Mavic Pro, there could be some things we've sort of discovered probably with the camera settings that make it look a little bit color value differently, but they look very similar from that standpoint. So everything that we've talked about, I didn't mention it, but if I even go back to this data here, we're basically just using the green part of the image. That image is red, green, and blue, and we're just using the green values of the pixels to come up with something like this. So if you look at red and green, those are visible. What if we throw in something that's not visible, such as near infrared? So if we look here, red, green, and blue are the typical visible pieces that we collect. Near infrared is another one that's very common. And we might even throw in another one that's right on the in the electromagnetic spectrum right on the edge of visible and non-visible light, and that's a red edge. You can see here the separation between the reflectance of where they're at. And one of the common vegetative indexes is NDVI, where we use the near infrared reflectance minus the red over near infrared plus the red. So here NDVI, healthy, the closer it is to 1, the value, the healthier the plant is. The closer it is gets to 0, the less healthy the plant is. So the near infrared is sort of more related to biomass, and then the red is related sort of the color of the chlorophyll in the case of a green plant that's out there. So there's been some work. This is some work that was done over across the way at Kansas State University, where they had a modified Canon camera to measure NDVI, and then they were using a handheld Green Seeker crop circle. I mentioned the OptiRx sensor that the producer had in the study that we did, sort of the same. Could we compare on-the-ground sensors to drone captured imagery? And then here's the imagery, and then the comparison between NDVI captured by the drone to the NDVI captured with the Green Seeker sensor, and it's very, very comparable between the two of how it's calculated. And even comparing NDVI with the drone to a yield map at the end of the season. Very, very comparable. So we've done some different things. We started out with this little sensor offered by Centera. Measures red and NIR bands, and then use a visible band. It's about not quite a $3,000 upgrade for a Phantom 4 Pro, but can be used on that type of platform. They do offer a sensor that has 4 discrete bands, visible bands, as well as a near infrared band. You just increase the value of how much you spend. So this is some initial imagery captured with the Centera sensor on some nitrogen plots at our Bradford Research Farm east of Columbia, Missouri. Things I just want to show you is if you see the 2 vehicles, that's a RGB image. This was captured with a Phantom 3 Professional and that single NIR sensor. You can see some others. If you just look at the infrared image, it doesn't show much, but if you combine the red part and the near infrared, then you get NDVI image that you can sort of shake out a lot further discreteness between the lower nitrogen treatments compared to the higher end treatments, and you can see how the bare soil looks compared if it's got a little bit of the soybean plots above it from that standpoint. So there's something to be said by adding near infrared or some other wavelengths to the mix and how we do some things. Another sensor we've been evaluating is a Parrot Sequoia, which has green, red edge, and near infrared. It's about a $3,500 sensor. It's sort of self-contained. It has a sunlight sensor, so you can compensate over a larger area the differences in intensity of sunlight in the pictures, and it has a GPS unit in that system, and then that's powered separately. And here's some of our initial data that we collected with that sensor, converting that to NDVI just on some forage plots. So you can see the differences in the vegetative index in some different varieties that were out there, and at least for a couple of those you could really separate. Now some of these, the NDVI image was about the same, so I couldn't tell the difference between Kentucky 31 and Martin 2 ProTech, but I could tell that the Bar Optima or the Tower ProTech was different than some of the rest of these varieties. So we're still experimenting on that side. One thing that we did do, so this is the same data except we're incorporating red edge. So red edge and near infrared wavelengths to calculate NDRE. In this image, you can still see the distinctions between the varieties, but now you see some streaks that are going north and south, and we discovered that was some fertilizer application error that had happened, and this was a way that we could verify that. If I go back just to the NDVI image, you can't necessarily see that, so pulling that from the red edge, we can definitely see that there might be some value in some other wavelengths and how we compare those kind of things. So we did some of the trials that we do might be related to nitrogen, and if you look here at this specific field over here up in this corner of this map on the right hand side of the slide, you'll see some different streaks. One of the passes is splitting the nitrogen application from 60 to 140, and then some of the passes got 200 pounds at side dress. And the idea from the imagery, can we see any differences? So if we look sort of over in the center of that field, if there was differences, you should be able to see some color differences out there, and it was sort of difficult to see that. So that was just a regular RGB image. What if we take it to the next step of NDVI, and you can still hard to see those kind of things that's out there. So that's using a Parrot Sequoia sensor. One other item that's being utilized specifically by a cloud-based imagery, drone imagery processing is Drone Deploy, and they develop what they call a plant health map, which actually is this vari index map which is usually just the visible portions, and just dividing them out in a different way that you get a map, a vary index. So this next slide is a vary index map for that same study, and you can sort of see some similarities. And if you plot the two together, values together, they're related pretty well. So if I go back and look at this map compared to this map, a lot of similarities. Where there's lower NDVI, there's lower vary index. Where there's higher, out here in the center, there's higher. So that's just a plot. It should be noted that the vary index does go into the negative, but it's more of a visual comparison. So some other areas, disease detection. This is a strip trial where we're looking at how we could use seed treatments to help us minimize the effect of a disease called sudden death syndrome. And you can see here the healthier strips alternating compared to the not so healthy, and that not so healthy didn't have a seed treatment, levo seed treatment applied at planting time to the seed itself, comparatively. At this height, this is at 100 meters, you can see the differences, but you really can't verify what that actually is until you get down on the ground. So getting down on the ground and flying lower, so our first attempt at doing this was putting some points or taking pictures along the way, and this shows where the pictures are. One where there's an area of infection, one where there's not so much, but you can still see that there's some plants. If we zoomed in far enough, you can almost verify that probably that is sudden death syndrome without even having to go completely to the field to verify that. Another methodology that we begin to use now is using another app. I mentioned MapPilot. This is an app called Litchi, where you can plug in waypoints and actually fly to those points and actually take pictures. So them smaller drones like a Spark or the Mavic Air have the capability of doing this and might allow you to do some different things besides just fly the whole field that's out there. So again, exploring indexes and their usefulness. This is that same field, except this is the vary index of that soybean field, and again it sort of visualizes things a whole lot better. This is an NDVI map of that, captured with the parrot sequoia, and then you can see that there was a pretty strong relationship between the vary index and NDVI in that field. The other thing that I decided to do in the end, we had the imagery plus we had yield data. So in this case, the strips that were treated yielded not quite 59 bushels an acre, and the strips that were not treated yielded 51.7. So a very statistically different between the two. So almost seven, let's just say 7 bushels an acre, and that easily pays for $10 worth per acre worth of seed treatment. So the other thing that I did in the end was I compared yield to the vary and yield to the NDVI, and again there was just very slightly a stronger relationship between vary and there was the NDVI, but both fairly strong relationship. So that sort of gives you an update, sort of where we're at as far as here at University of Missouri and through our extension program, where we're at using the drones and the type of drones that are out there to move forward in some of this information that we can capture and then actually turn it into a decision, such as a nitrogen management standpoint. So that includes this part of the presentation. And I also have a presentation that will come following this related to an update on the rules we have for flying drones.